Hello folks, welcome back. Our topic today is assignment 21, which is all about finding the max and mins, finding extreme values of a function. And in my time of teaching calculus, when we first began there were no graphing calculators. Everything had to do by hand. It's true now that a lot of the questions that we once did by hand can now be solved using the graphing calculator in Algebra 2. I think it's still very important and helpful for calculus students to have a pretty good idea of what the theory and the mathematics and the calculus is behind answering these questions. So we've already talked a little bit about how we go about finding extreme values. We try to examine critical points where the first derivative is either 0 or undefined, and also when the function is defined on a closed interval to examine the function at the endpoints. There's a terrific little strategy in the textbook that I have grabbed here, and it's right here at the bottom of our page, and it's all about a 6-part step, and each part is really important, and I stress it to my students. So the first one, make sure you understand the problem, and the way I try to describe that is know enough about the problem so that you can close the book and explain the key ideas to somebody who's sitting next to you. The next part is to try to draw a picture, a diagram whenever possible, and make sure that you have covered the key aspects of the problem. Then you want to make sure, obviously, that you graph the function, and of particular importance here is finding the domain of the function. And a lot of times that will be a closed interval, and that indicates that you're going to be looking for the endpoints. And that's really what the next part is all about. We want to make sure we look at what the critical points are, and we want to make sure that we consider the endpoints. You then basically solve this model, and finally you interpret the solution, and by that we simply mean to answer the question in a full sentence, and of course think a little bit about whether your answer makes sense. Okay, so let's put these ideas to work with this example where we're trying to find two numbers whose sum is 20 and whose product is a maximum. Well, if one number is x, the other number has to be 20 minus x. And so therefore the product of these two numbers is x times 20 minus x. And that's what we want to try to find the maximum value of. Now, as I said before, this is a problem that actually can be handled by Algebra 2 students. So we'll look at two different ways of approaching this. If I want to graph this function, I know it's already in factored form. So there's a root at 0 and there's a root at 20. I also know enough to know that this is a quadratic function. P of x is equal to 20x minus x squared. So it's a parabola opening downward. I know everything about parabolas, and I know that the graph will look something like this. However, since I need to have these two functions, these two numbers, add to 20, that means it's only this part of the graph that I'm looking at. Other than that, the numbers will not add up to 20. And so, any student can look at this and say, well, the maximum value occurs right about there. And most students at this point know that for a quadratic function, the vertex is located halfway between the roots. So that means that x has to be 10, which means 20 minus x has to be 10, and so the two numbers are simply 10 and 10. Pretty simple, and as I said before, we could actually have students in Algebra 1 that have had the quadratic function know how to solve that. So if we want to solve this now using calculus methods, we go back to our function, and we look at the derivative, and the derivative is simply 20 minus 2x. So where does that equal 0? So p prime of x equals 0 when x is equal to 10. And what we can do here is then look at the second derivative, and the second derivative is minus 2. So since the first derivative is 0 when x is 10, and since the second derivative is negative, what that tells us is we have a max when x is equal to 10. And then we should answer in a full sentence. The two numbers are 10 and 20 minus 10, which equals 10. All right, good enough. Okay, so let's look at another problem. And this one asks, how close does the graph of y equals the square root of x come to the point 3/2, 0? And so what we'll do is we'll make a little sketch of this. And here's the graph of y equals the square root of x. And here's the point 3/2, 0. And so what we say is, let's just look at the distance or the length of the segment from 3/2 to any point on here. And to force that point to be on the curve, we give it as coordinates x, square root of x. So what we know now is that this distance between these 2 points is equal to the square root of x minus 3/2 squared plus the square root of x minus 0 squared. Now, it's very important to, well, not important, but it's helpful to notice that this is positive, this is positive, and we're adding these two things together. So to find the smallest value of this expression d, it's enough to find the smallest value for just this, because this is what we're taking the square root of. So that makes life a lot easier. And so I want to minimize d, capital D here. So I take the derivative, and using the chain rule I get 2 times x minus 3/2 to the 1 times the derivative of x minus 3/2, which is 1, plus the derivative of x, which is 1. And so this becomes 2x minus 3 plus 1. So the derivative is equal to 2x minus 2. And the second derivative, while we're at it, is 2. So therefore d prime equals 0 when x is equal to 1. And because the second derivative is positive, that implies this is a min. So the point there on the curve where the distance is a minimum is going to be 1, 1. And if we go through the work of finding what d is, we will learn that the value for d is the square root of 5 over 2. And there we go. And that's probably enough examples for you to get an idea of how to work these problems. And so we'll conclude this lecture right here. Thanks. See you next time.